All right. So section R1, units of measurement. There are 7 SI units of measure. SI stands for the System International, and these are what the science field, all sciences have decided upon as the main units of measure. You have any number is nothing by itself. If I just say I'm 3, what could that mean? It could mean I'm 3 days old, I'm 3 years old, I'm 3 years into my job, I'm 3 feet tall, I'm 3 pounds or kilograms or whatever, or I'm 3 days away from doing this test I have to do, or whatever. A number is meaningless. You need to have units. And so those units have to be standardized in a way that anyone around the world can read it and understand what it means. So we have these 7: mass, length, time, temperature, mass, length, time, temperature, electric current, the amount of substance, and luminous intensity. And I'm going to go over the true scientific definition of each of these, but also keep in mind the symbols used to signify each of those units of measure. Mass is measured in kilograms, length is measured in meters, time is measured in seconds, temperature is measured in kelvins, and electric current is measured in amps. The amount of substance is measured in the mole, and the luminous intensity is measured in candelas. These 3, the kilogram, the Kelvin, the mole, those are the 3 main units of measure that will be used in this class or by any chemist in general. So the meter is defined as the length of the path traveled by light in a vacuum during a time interval of 1, essentially 300 millionth of a second. That's obviously a very, very, very tiny frame of time, but light in a vacuum will travel 1 meter in that amount of time. And the reason that it has to be defined by light is that really the original definition of the meter was 1/10,000th the distance from the North Pole to the equator. And the problem with that is that Earth is not a perfect sphere, so different parts of Earth would have different distances, and so it doesn't really work. And the size of Earth is always changing, actually, because there's always meteors bombarding Earth, and so it's actually growing, and so this wouldn't work forever. But the speed of light never changes in a vacuum, so this is something absolute and definite, that light will travel that far in that amount of time. The second is defined as the duration of 9,192,000,000 and so on periods of the radiation corresponding to the transition between 2 hyperfine levels of the ground state of the cesium-133 atom. Again, this might seem weird. You all intuitively know what a second is, but in science there has to be a definite, unchanging definition of it, and the problem is that time actually is relative, and we can thank Albert Einstein for that idea. You may not know what it means, but I'll try to explain it here. If you take 2 clocks and you synchronize them together, and you leave one on Earth, and you take the other one and you put it with an astronaut, and you send it up into space, and you let it stay up in space for an extended period of time, and then bring it back down, the clocks will no longer be synchronized with each other. In fact, the clock that went up into space will be behind the clock that stayed on Earth. And this study has been done multiple times. But as it turns out, the faster you move, the slower time moves for you. Time is relative. This is why it's the theory of relativity. And so we can't really judge time properly because we're always moving. The Earth is orbiting the sun. The Earth is rotating around its own axis. The sun is orbiting around the black hole at the center of the Milky Way galaxy, and the Milky Way galaxy is moving in space as well. We're always moving. But if we were to go from Earth to a different planet or a different spot in our galaxy or universe, we might be moving at different speeds, and therefore time would be different in how we experience it. However, a cesium-133 atom is going to, which is radioactive, is going to radiate 9 billion and 200 million or so times every second. What we know a second to be here. So this is where the term atom clock has come from. They use how many times something like a cesium atom radiates, and they use that, since it's exactly that number, they use that to define time. Now, this isn't something that you will be tested on, these ideas, and I really only show for all of these base units how ridiculous it is, because I like to impress upon my students the importance of how science works and how exact things are, and being precise and being accurate. And it's obviously, these definitions are, especially the next ones coming up, are challenging to comprehend, and they're weird and way too picky, but that's what you get with science sometimes. The kilogram will soon be redefined as the mass necessary to make Planck's constant, which we will discuss later in this semester, but not in this lecture itself. And so it'll be the mass necessary to make Planck's constant exactly 6.62606 times 10 to the negative 34th, when expressed in the units of kilogram meters squared per second squared. And you can see there's kilograms in there, and we'll get into what the units of Planck's constant normally are expressed as later, but it's making that value exact. And you can see it's got meters and seconds in there, which are already constant values. So that gives us just the kilogram. The next unit is the ampere, which is the measurement of elementary charge. It's soon to be redefined as exactly 1.60217 times 10 to the negative 19th amp seconds, which is equal to 1 coulomb, the measurement of actual charge. But amp is the base unit, and there's seconds in there, which makes this, again, constant and defined, or definite, because it is based on the second as well, essentially. The Kelvin is going to be redefined soon as well, and it'll be done so by setting the numerical value of the Boltzmann constant exactly equal to that big giant number right there, times 10 to the negative 23rd kilograms meters squared per second squared per Kelvin. Again, everything else in there, the mass, the meters, the seconds, those are definite values which can't change. So if they set Boltzmann constant exactly equal to that, we get just kelvins. We won't go over the Boltzmann constant in class or anything, but if you were to be a chemistry major and take higher levels of chemistry, it would be discussed at some point. The mole is soon to be redefined by fixing the numerical value of Avogadro's constant to exactly 6.022 times 10 to the 23rd per mole. And what that means is, like, if you have 6.022 times 10 to the 23rd atoms, that would equal 1 mole of atoms. And as another point there, 6.022 times 10 to the 23rd is 602 hextillion. So if it's atoms, you have 602 hextillion atoms, which is obviously a number you can't really fathom how many that is. It's so huge. The candela is soon to be redefined by fixing the numerical value of the luminous efficacy of monochromatic radiation of frequency 540 times 10 to the 12th hertz to be exactly 683 seconds to the third power. Candelas, sterans per square meter per kilogram, which is equal to a lumen per watt. Obviously, the standard candela is really supposed to be the amount of light that a candle gives off, 1 candela, and so that's what that is supposed to be.